look at it and see what is going to happen. And you know, mentally, this is the best example of field prediction. Imagine nobody was knowing at that time when he was actually giving his study table that electron is a particle in nature. He was not knowing that. आज अगर हमको कोई पूछे how do you explain periodic table, you will say we know the electronic structure and you can always understand that if this is the kind of electronic structure, these elements fit in this particular group. He was not knowing that. He was only worried about one thing. He was a teacher and he was teaching chemistry to his students. And he was worried that now I have to teach hydrogen separately, I have to teach lithium separately, I have to teach potassium separately. Can I do one thing that I just tell them about one element and then they are able to understand all other elements? So he thought of, you know, looking at various elements which were known at that time, which were 64 in number, and he saw some pattern emerging. And that is why we normally say that science is nothing but the study of patterns in nature. And during those patterns, when he was, you know, putting various elements in their different places according to their properties, he found that certain places have no element of that kind which can be fitted here. Gallium was, for example, one example. And he left that space vacant. So this is called intuition. That there must be this kind of element which you should find in nature and you should fit it there itself. And there are very few, you know, people like him who could in their lifetime see their prediction coming correct. There was a man whose predictions actually came correct. So prediction is very important element of the part of a scientist's work. Try to imagine if Oersted had given a prediction that if you have a current, a conductor in a magnetic field, you should be able to see the current. Currently would have not been left with anything to search for, but he didn't make any such prediction. Because like, you know, possibly what you see, what is going to happen in future. Then many times, you know, there are certain very interesting approaches which people follow to discover something. The discovery of graphene is one such example. Here we find that something which people had said is not possible because they had theoretically proved it that this is not possible. Somebody said, no, let me see and try to do something by which can I say that that kind of a thing is possible or not? Now, when I am saying something not possible, what was that thing? Let me tell you that. That was this, that two-dimensional crystals are not possible because of thermal instability. And why bother about it? Don't just waste your time in looking for two-dimensional. This was the approach, and it was in 60s that a paper had been published in which this was conclusively done theoretically. But theory has got no meaning unless your theory matches with the experiment. So this fellow, Andre Kim, and one of his students, they were actually working together in Manchester. And they were actually looking at layered materials. Like, for example, graphite is a layered material. If you tell students that it is nothing but a layer of carbon atom, another layer of carbon atom stacked on top of each other, and that is what makes graphite. And this fellow was thinking, can we really peel a layer out that will be a two-dimensional system? So he had put one of the students to a task. He gave him a graphite crystal and he said, you know, try to rub it and see whether you can peel off one layer of that atom. Nothing of that. उसने चमका दिया graphite का crystal, but nothing came in his hand. So one day, Game did what? He went to the market and bought Scotch tape. Scotch tape आपको मालूम है? वो cello tape जिसको हम बोलते हैं. And And then he said, let me really paste this scotch tape on protein and let me peel it off. And let us see what happens. And to his surprise, what he found was that one layer had stuck with that shallow tape, and they tried to look at it under a tunneling electron microscope, and to his surprise, what he found was here is a two-dimensional crystal. कभी किसी ने ड्रीम भी नहीं किया, but this is exactly what was happening. If you observe things in nature, you will find this very often happening. You will find that when people cut wood, there are certain directions in which wood can be cut very easily, whereas there are certain other directions in which wood cannot be cut easily. So there are cleavages between which you can easily carve, and if you cleave along those directions, things will come out. And what was so interesting was also this chemically, that in the layer, in a two-dimensional layer, the bonding is very strong. That is covalent bonding. But across layers, the bonding is weak, which is van der Waals bonding. And as a result of that, you are knowing that layer will not get disturbed, but two layers can be actually taken apart. This is exactly what happened in the case of this approach. अब ये ना ऐसी approach है जिसके लिए आदमी को झपकी होना पड़ता है. Then and only then one can see this kind of thing. And now I am going to tell you another thing which is happening today is the state of the art technology which we should have. When we are talking of doing computation, for example, we are saying that today I can do it on the laptop. Arun said that, we can do it on the laptop. Reason is that the state of the art technology has come to such an extent that tomorrow you may find you will say that I am doing my DSC calculations on my mobile. That day is not very far. That kind of a thing is going to happen very soon. So, when we were talking about Higgs boson as the most fundamental particle of nature, we were not able to find it despite its prediction in 60s. And everybody was saying that you must find this particle. What was the limitation? The technology was not ready. We didn't have that kind of energy available to us, that scale of energy, where we should be able to see in some scattering experiment the production of Higgs boson itself. Now, this Large Hadron Collider, which is operating at greater than 7 GeV electron volt, we were finding that that is the kind of technology which was needed, and it took some time for that to happen. I can give you numerous examples, from physics itself, that why these technologies happen, and when they come, we suddenly find that something is known to us. Like, for example, electrons. When I was sitting in the morning with Nina, she was talking that we found induction coil also in our lab, old induction coil, which we had just put it in our storage. Induction coil played a very important role because to cause discharge in a discharge tube where two electrodes are there, you require higher potential. DC potential of the order of 15,000 volts or 20,000 volts. How would I produce that? So induction coil was one such device with the help of which you can produce those high potential differences, and if you bring two needles of the induction coil together, you can see the spark passing because of that high voltage which is there in the breakdown of the medium. So state of the art technology actually makes lot of role in doing that. So what were the state of the art technologies which were going in search of the electron? How to create vacuum, discharge tube में vacuum चाहिए, how to change that vacuum pressure inside the discharge tube. Then that there were different stages in which people studied what is happening inside, say, Cook's tube. And it took almost 150 years for that kind of a technology to develop. And once it was in place, J.J. Thomson came out on the scene. He set up an experiment and he could find a charged particle which was part of a neutral atom. And the moment he knew that, he said, atom has got at least two things I am sure of. One is electron, other is positive charge, which is neutralizing it. And he gave his famous model called that plum pudding model. That pudding is like a positive background and plums are sitting in it like it. Okay, and this is how modeling comes. And then uh, somebody came to him and he was his student only, Rutherford. He said, I want to test your model. क्या ठीक है टेस्ट करो साइंस में तो ये चलता है so he came with an experiment in which he threw alpha particles on a gold foil and he found there is no uniform positive background like pudding. There is not a vacuum in between. So Rutherford said there has to be a nucleus in which positive charge is sitting. Rest of the atom is all empty and electrons are around that nucleus only. But there was one problem in his model when he said around, and if they are revolving around it, they are accelerating charged particles actually give out energy. This electron should fall inside the nucleus. That was not happening. And that was a moment for Bohr to bring a model, a new model, in which he said, I know that where it will not fall inside the nucleus and when will it fall inside the nucleus. So he talked about those stationary orbits. He called those as stationary orbits. So, all these things happen slowly and steadily. So I talked about Brahe, Kepler, Faraday, Mendeleev, and Wien, who are part of this culture of what you call how scientific knowledge actually progresses. Next, please. So, what has actually caused in a present scenario in computational material science or in physics or in chemistry or in biology? Somebody, a news was asking me, आप nanotechnology में क्या करने वाले हैं? Then he asked me a very interesting question कि सर drugs के साथ हम इसको कैसे use कर सकते हैं? When we were talking about that problem of drugs which is happening in the institution, I was finding it difficult to answer that kind of question. क्या बोलूँ मैं क्या बताऊँ? Physics वाले क्या expect करते हैं? But okay, what we have observed is that when we started doing these computational material science, we found that the pace of discovering new things has moved very fast. Never in the history of science that we were discovering every day new material. हमने आज जो material science में progress हुई है, उसके काफी कुछ रोल computational aspects का रहा है, नए से नए materials को discover करते हैं. And that is what is the focus of this particular workshop also. We are going to do computational things maybe related to nanomaterials. Those can be layered, single layer, double layer, a one-dimensional thing, one-dimensional material, or you can also think of bulk materials, and you would like to do something with those bulk materials and see that how by doing this thing, the properties of this bulk material is changing. For example, you add some impurity, you remove some atom, you create voids, you create vacancies, you create some kind of a, what you call a cleavage with the help of an accelerator by letting that material hit by what? By hitting it by, say, very fast particles. I hope you are understanding what I am trying to say. So, we were finding in the beginning of the last century, that is the 20th century, things started moving very fast. But it was not as fast as this is today. And this actually happened because of better and better understanding of quantum mechanics. So, till the beginning of the decade of 20s, we were stuck with the semi-classical thing. But the moment this decade came, there were different people who were working on different ideas. Schrödinger came out with wave mechanics. Heisenberg came out with matrix mechanics. Dirac also tried to follow them. They were simultaneously working together. And he was also working on matrix mechanics itself. And to his frustration, what he found was that same problem which he was doing had been solved earlier by Heisenberg. So he was left high and dry on the wood because when you do something, you would like to be the first in doing that. So better understanding started coming from quantum theory. Also, there were new technological tools which have emerged, which let us see deeper into the material, like atomic force microscope, scanning tunneling microscope, electron microscopy, and different ways by which we are doing nanotechnology these days in the lab. And we find that with the lab, simultaneously, my offline computing resources were available. Let me tell you my own journey into it because that will be very interesting to appreciate and understand. Computers came in 1984, roughly in India's scene, particularly laptops. I was one of the persons who was very much interested in having a computer. So by 1992, I was having my own personal computer with 4 MB of RAM and 40 MB of hard disk. And we were running it by means of a floppy disk, 3.5 inch. The beauty of that operating system which Bill Gates provided to the market was this, that with very meager resources, you could do a lot of things on that personal. Okay, so this is a very interesting thing. I had spent almost 1 lakh rupees in buying that machine. Managing. But I know that I did because the thing which was real fact in the operating system was basic language. Okay, we said why not do physics with our students using this basic code? And we did that. In fact, it was very interesting that using basic only, we could publish a book on computational physics. Just imagine. Meager resources, but maximum mileage we try to get out of it. Today, when I am talking of computing resources, I think today your laptop, which you go and buy in the market, is as good as a good computational machine with very high resources. And I think in this workshop you will hear a lot about it, that what are the things which you need for making yourself part of computing, spaces. I'm not saying computer wala. I am very much underlining the word physics wala, because for us it is physics which is actually going to be very important. And when I left the department in Himachal Pradesh University, we had this high performance computing facility with about 128 cores, जो कि आज की डेट में तो ज़्यादा नहीं, वो भी हम पीछे रह गए. But it is still very good. We were talking about a laptop, and if that resource is there in the department, I think that can be used by very many people. Provided people let us use that. Many a times, people don't let you use things which are available in the department. They will put a lock on that, and they will not let you know that what you can do, what are the resources you have. But this computer, has brought an interdisciplinary approach into the process. Like physical sciences, chemical sciences, you will find I'm a physics wala, Jeffrey is a physics wala. He is publishing his papers in journals of chemistry. Why? Because सबसे ज़्यादा फायदा क्वांटम थ्योरी का बिगिनिंग में मालूम है किससे होता है? एनर्जी. All of the mystery behind the periodic table was removed once we understood the quantum mechanics of the atoms. We could start, understanding what is happening. Now there is a very interesting quote, which was given by Dirac, and that quote is the following. The fundamental laws necessary for the fundamental treatment of large parts of physics and whole of the chemistry are thus fully known. And the difficulty lies only in the fact that application of these laws leads to equations that are too complex to be solved. What is that equation? Differential equation. Too complex to be solved. उसने ये कहा कि हम कर सब कुछ सकते हैं, but complexity इतनी ज़्यादा है that we cannot solve it. The reason is very simple. As the number of electrons are rising in the system, solution of the Schrödinger equation becomes more and more difficult. And we were not knowing how to overcome this. And there were, people who were the cleverest among, physicists. who were coming out with these ideas even during that time. One of such persons I would like to mention is was Fermi. I hope you have heard the name of Enrico Fermi. And maybe you might have heard Thomas Fermi model. This guy he was the person who first of all tried to talk about instead of electrons as separate entities, but as electron density. Okay. So, in the beginning, when people said hydrogen atoms, तो आप explain कर लोगे. What about when you have a very heavy atom? Can you explain its, that electronic structure? He said, yes, if you try to think not in terms of electrons, but in terms of electron density. This electron density is the most important thing in that density functional theory. And what happened as a result of this was this, that you can handle a 3n coordinate problem into three-dimensional problem. That you are not dealing individually with each electron, but you are dealing with the density. So then you say, what is the meaning of an orbit? The orbit is where you will find some or the other, the density of finding electrons is 4, another orbit again, in between there is a vacuum. And he was able to explain along with Thomas, that is why it is known as Thomas Fermi model, that yes, we understand what is the kind of structure which these multi-electron systems. So the basic idea behind density functional theory is coming from people like Fermi. Next please. Now, this is how things start happening. And people started cracking this problem of a truly many-body problem. And when we have a truly many-body problem, what we have to do is, we have to think in terms of what you can call statistical mechanics. But it is not as easy to apply statistical mechanics here also, in the case of, say, atoms or materials. So, this progress was, slow and steady, but it was working. For example, in MSc courses itself, today, students do hydrogen atom, and then they try to go to multi-electron system. They do that. Like, for example, they try to go to sodium. And sodium has one very typical spectral problem that it has got two yellow lines. How to explain those two yellow lines? This you are able to do without going to the density function. But still the problem is very complex. So you start seeing some constraints happening when you are working on those things. And there were, a very interesting set of people who tried to crack those problems without any computationally big resources. One such team was of father and son, Hartfield. And what they did was that son tried to create that model, like how to manage this, and father did calculations for him. And that was happening immediately in that decade of 20. That led to what we call as the Hartfield. But then you will find that people were not very happy with this Hartfield theory also, because they were finding that the properties of the wave function which are emerging out of it, that was not taking care of a very important aspect of the wave function of an electron. And that was that it should be antisymmetric. And it came from Pauli's exclusion principle. Actually, quantum mechanical definition of the Pauli's exclusion principle is this, that the wave function of an electron has to be antisymmetric. And Hawke came on the scene, added that element into it in 1930, and gave us a theory which was quite comprehensive, but it had to stay till 1950 when we started having computers. This was the time when people started talking of having a computer for doing physics calculation. And from where did the computer emerge? Let me tell you that also. 1940s decade was a very bad decade in the sense that World War II was going on. And whole of the physics fraternity in USA was concentrating only on one thing. And that was how to make an atom bomb. And in making that atom bomb, they were actually creating computers on which they should be able to do simulation, particularly of Monte Carlo method, to see what is the critical mass which is needed for the fusion to occur and chain reaction to take place. So all the modeling was done on the computer. So when that World War II was over, we were coming into 50s, we were starting saying, my पास तो computers भी है, you can use it for different purposes. As we are saying today, आपका laptop है ना तो आप DFT कर सकते हैं. That is what is the message which is going to come out of this workshop. And then people talk of variational method using computers, Monte Carlo method, quantum Monte Carlo method, for example, molecular dynamics approach, classical as well as quantum mechanics. Classical happened in the decade of 1960, and one Indian born scientist, A.R. Rahman, he was from Osmania University, later he went to USA. He was the first person to do a classical molecular dynamic simulation for argon. He was the first person to do that. And when I am saying classical, as we see Schrödinger equation of motion in the case of quantum mechanics, Newton's equations of motion play the same role in the classical molecular dynamics. So it was a question of knowing a potential, making use of that potential to find the force, which is nothing but the negative of the potential gradient of the potential itself. Make use of that to solve that equation to find position and velocity. So ultimately, what do you get? You get position and velocity. And you require a good computer. I remember it was in 86, 87 when I had joined university and I was looking for a problem to achieve the problem with उस पे काम करते हैं. जैसे आप इस वर्कशॉप में आए हो ना, एक चंडीगढ़ में वर्कशॉप हो रही थी पंजाब यूनिवर्सिटी में, I went there. And in that, for the first time, I heard about this classical molecular dynamics. तो जिसने लेक्चर दिया था वो इंडियन ही था, प्रोफेसर अरविंद कालिया करके इनका नाम था. मैंने उनसे पूछा ये हम कर सकते हैं काम इंडिया में? उसका बड़ा एक बोलते हैं ना, लाइफ का पॉकेट, बस इसके लिए बड़ी मशीन थी, you cannot really do it. तो फिर हम अपने जो काम कर रहे थे उसके ऊपर वापस आ गए. ऐसा नहीं था कि हमको वही करना था, बट ये जो पीड़ा था कंप्यूटर वाला, ये छोड़ नहीं रहा था. ये दिमाग में घुसा हुआ था कि हमने कंप्यूटर कभी इस्तेमाल करते हैं, तो इसीलिए वो कंप्यूटेशनल फिजिक्स वाली लाइन पकड़ी. उसका एक बड़ा फायदा हुआ. बिकॉज ऑफ दैट एक्सपोजर ऑफ दैट स्मॉल कंप्यूटर, I got a fellowship from Edinburgh. That was actually a Commonwealth fellowship, and I had 1 year exposure of doing this calculation on a supercomputer. और उसमें ना हमने चीजें सीखी, सूडो पोटेंशियल कैसे यूज करते हैं, कैसे जनरेट करते हैं उनको, उनका रोल क्या रहता है इन कैलकुलेशन में. यू विल हियर अ लॉट अबाउट दैट आल्सो इन दिस. और जब मैं 97, 98 की बात है, मैंने केम बैक, फिर वही बात कि मेरे पास वैसा कंप्यूटर तो है नहीं, मैंने अपना एक साल जाकर के वेस्ट कर. रिमेंबर वन थिंग, यू नेवर वेस्ट एनी टाइम व्हेन यू स्पेंड ऑन समथिंग. And Arun is sitting here, I believe, or not? Yeah, he is here. When he was to do his MPhil, तो हमें ये लैपटॉप थे हमारे पास, और एक मेरा और स्टूडेंट था पुराना, तो जर्मनी में था. उसने कहा था एक कोड है CS का, ये लैपटॉप पे चल जाता है और ये कैलकुलेशन कर देगा. और उसके लिए हमें सबसे पहली चीज जो लर्न करनी थी वो था हाउ टू जनरेट रिलायबल ट्रांसफरेबल सूडो पोटेंशियल. एंड हिज एंड रिजल्टेशन वाज दैट. हमारे पास एक कोड था, उस कोड की मदद से हमने वो जनरेट करने शुरू किया. I hope now you are seeing that progress, how this happens as we actually move further and further. तो ये हमारे पास जो सूडो पोटेंशियल, ये इनको हमने एवोल्यूशन सूडो पोटेंशियल बोल रहे हैं. I was working in liquid metals and alloys. There was one student, he is also teaching in a college in Solan, Dr. Anil. He was also working with me. So I said, हम तो बॉर्डर सूडो पोटेंशियल इस्तेमाल करते हैं इस प्रॉब्लम के लिए, वो नहीं हम यूज करें. We will use ab initio pseudo-potentials to see that how properties get out by using those things which are ab initio pseudo-potentials. Where you don't assume anything with the inputs which go are very interesting. But these when we are talking of all these things, pseudo-potentials, for example, if you ask me in nutshell what is physics, I would say physics by name is approximation, but not just approximation, but intelligent approximation. And pseudo-potentials, model pseudo-potentials are such intelligent approximation. And we had a way to produce those pseudo-potentials with the help of computers itself. Now instead of just modeling the parameters. So this was regarding molecular dynamics part. Classical molecular dynamics came in 1964, but it was in the decade of 80s that people started talking about quantum molecular dynamics. तो एक खास पैनल लोग तैयार किए थी, इन्होंने मिलकर के वो क्वांटम मोंटे कार्लो के बारे में काम करना शुरू किया। In the meantime, from 60s के decade से एक आदमी था जिसका दिमाग डेंसिटी में घुसा पड़ा था, who was always thinking in terms of density, and that man was this man with the cap, Walter Cohen. कोहन शाम थ्योरम जब आप ना डीएफटी की कुछ चीजें पढ़ते हो तो उसमें इसका नाम आता है। इस आदमी ने दो थ्योरम्स प्रूव करके कोहन के साथ मिलकर के बताया हुआ था कि आपको अगर एक प्रॉपर डेंसिटी मिल जाए तो आप ग्राउंड स्टेट प्रॉपर्टीज को बड़े आराम से समझ सकते। दिस वाज द एसेंस ऑफ हिज वर्क, एंड द ब्यूटी ऑफ दिस वाज दिस that three-dimensional problems by his approach, which Thomas Vernet was also talking about, get converted into three-dimensional problems. और ये लोगों के साथ जाकर के ना बोलता था ये ना मेरे आइडिया को आप कंप्यूटर में कन्वर्ट करके जरा यूज करके इस स्टोरी में मैं आपको वो स्टोरी भी बताऊंगा कि व्हाट वाज हैपनिंग। सो नाउ दीज आर द पीपल कार्ल कार्नेलो, श्रोडिंगर, हार्ट्री, एंड हियर इज प्रोफेसर A.R. Rahman, who actually did these classical molecular dynamics. Next, please. Now, let us try to see उस decade में जिसमें मैं computers learn कर रहा था क्या हुआ? What happened? Beyond 1990, we were finding ये जो जिसको हम बोलते हैं एक एक्सपेरिमेंट थी ना, एक हम टर्म इस्तेमाल करते हैं खास करके बायोलॉजी के लोग बहुत इस्तेमाल करते हैं, इन सिटू अप्रोच एंड इन सिलिको अप्रोच। इन सिलिको का मतलब है कंप्यूटर पे करके देखना, इन सिटू का मतलब है लैब में करके देखना। और ये जो 1990 के बाद जो कुछ हुआ उसमें क्या हो रहा था, कंप्यूटेशनल पावर ऑफ द कंप्यूटर एंड देयर अवेलेबिलिटी एज डेस्कटॉप वाज इंक्रीजिंग। There were some novel computational methods which were coming up, which were field specific. बायोइन्फॉर्मेटिक्स का नाम आपने सुना होगा, बायोलॉजी वालों के कोड उसमें बड़े हुए थे। गॉसियन का नाम आपने सुना होगा, केमिस्ट्री वाले उसमें काम करते थे। ऐसे ही हमारे पास सिएक्सा है, ये फिजिक्स वालों ने डेवलप करा। ऐसे ही क्वांटम एक्सप्रेस हुआ, ये फिजिक्स केमिस्ट्री दोनों के साथ चलता है। और एक कास्टेप कोड था बड़ा फेमस कोड जो मैंने ना एडिनबरा में इस्तेमाल किया था, दैट वाज बेसिकली फॉर फिजिक्स प्रॉब्लम। तो ये धीरे धीरे लोगों ने ना ये कोड बनाने शुरू। Now there was one more thing which was happening here. People realized the importance of one fact, that this kind of work cannot be done by individuals, but it has to be done by teams. Teams will have to come together and do. आपको कोड लिखना है तो सिंगल आदमी नहीं वो कर सकता, टीम करेंगे। आपको डिफरेंट लाइब्रेरीज क्रिएट करनी है। I think that is the kind of culture which needs to be brought to India. अभी भी हमारे पास वो कल्चर नहीं है। हम ये नहीं कह सकते कि कोई इंडियन कोड है जो कि इंटरनेशनली अवेलेबल है जिनको हम यूज करके एजुकेशन कर सकते हैं। एंड देयर वाज अनदर थिंग व्हिच वाज इमर्जिंग, दैट वाज ओपन सोर्स कोड। मेरे जैसे गरीब आदमी जिसके पास पैसे नहीं क्या करेगा, कोड आता है $5,000 का, कहाँ से लाऊंगा? So we were looking for these open source code, and CSA actually qualifies for that. That is why we are talking about this. And today there are a number of such beautiful codes. Quantum Espresso is one such code. Maybe in future, अगर Arun and Rajendra ji चाहेंगे, so they would like to do a workshop on quantum espresso itself. Maybe that will be second step to this particular concept. Now, there is one thing more which you should realize that after the usage of computers in physics, 60s में हम यूज कर रहे थे, रहमान ने यूज किया क्लासिकल मॉलिक्यूलर डायनेमिक्स करने में. How the cost was changing, how the speed was changing, how the memory was changing, how the size was changing. In 1967, cost was $50 million and speed was 0.1 megahertz. Memory was 1 MB, size was small. Try to imagine this. Then in 2013 when we came, our cost had come down to $4,000. आजकल यूएस से जाना हो तो $4,000 का किराया लगेगा, है ना? And speed was 1 gigahertz. Memory was 10 GB. ये मैं 2013 की बात करता हूँ. Size लैपटॉप. आज की डेट में मेरी डेट में जो मेरा मोबाइल है उसमें जो मेमोरी है that is 256 GB. इतना बड़ा कंप्यूटर मैं जेब में लेकर के घूमता हूँ. इमेजिनेशन. तो चेंज जो है ना यहाँ से यहाँ तक आने में ये ऑफ द ऑर्डर ऑफ 10⁴ है. अगर हम इमेजिन करें, दिस इज ए interesting comparison which I took from a Nobel lecture by Michel Lewis. Is that if cars were like computers, then a new Volvo would cost $3. I don't think speed technology would have a top speed of 10⁶ kilometers per hour, would carry 50,000 adults, and would park in a shoebox. A very interesting comparison is there. हम कहाँ से कहाँ the transition which we have made is huge, unimaginable. Next. And here is a very interesting fellow, John Popple. ये जो है John Popple, इसकी हिस्ट्री, इसकी जो टेक्निक हिस्ट्री है बड़ी इंटरेस्टिंग. He was a kind of a rival to Walter Koch. And इस आदमी ने वाल्टर कोहन के उस ड्रीम पे काम करना शुरू किया, which was this, that can somebody come and develop some codes, computational methods, and he started working on that in quantum chemistry. And we found that he also got a Nobel Prize along with Walter Koch in 1998. And you know, there used to be conferences in which Walter Koch will be there and Popple will be there, and Popple will stand on the dais and say that why Koch's way of doing things is not appropriate. Okay, kind of a comparison going on. And he, in fact, in one of the conferences listed 10 points where he said that what Cohen is saying is not working in that way, the way it should work. But Nobel Prize मिला तो दोनों इकट्ठे जा रहे थे Nobel Prize देने. Okay, so this is one thing. And then we also found ये जो कार्टून है ये ना हमारी एक मैगजीन है बहुत अच्छी, this is called Resonance. You might have heard its name. It's also available on the internet free of cost. You can download everything. It is open source, open accessible. उसमें एक कार्टून छपा जिसमें ये जो पोपेल है ये बैठा हुआ है, कंप्यूटर पे काम कर रहा है, और he was the man who was responsible for creating Gaussian code. Okay, Gaussian code आपने कुछ लोगों ने जो डीएसपी पे काम कर रहे हैं यहाँ पे बैठे होंगे उसके बारे में, केमिस्ट्री वालों का बड़ा फेवरेट कोड. एंड इसने वो सॉफ्टवेयर बनाया और ये अनफॉर्चुनेटली कैसे लेता है, इसके फ्री नहीं दिया हुआ है वो कोड. You have to buy this code once again. Or what he did was he tried to calculate certain things which were happening happening in the molecules in the interstellar space, co-stimulation is originated. Or his contribution is actually shown here in a very interesting cartoon itself. And एक बड़ी इंटरेस्टिंग चीज मैं और आपको बताऊं, वैसे नोबेल प्राइज किसको दिया जाता है? आमतौर पर उस व्यक्ति को नोबेल प्राइज दिया जाता है who has discovered something new. But in the case of this Nobel Prize in Chemistry to Martin Karpolov, Michel Levitt, and Elliot Schwarzschild, they were given a Nobel Prize for developing methods that can be used for chemical studies of the properties of molecules and the chemical process in which they are involved. कुछ डिस्कवर नहीं किया, कोड बना के दिया, आप उस कोड को इस्तेमाल करो और देखो आप बहुत कुछ अंडरस्टैंड करो. This is one of the instances in the history of the Nobel Prizes where if you say that what did you do? आपने क्या डिस्कवर किया? They have no answer. They say we have made a machine which is a computing machine with the help of which you can discover anything. And hallmark of these developments has been predictive in nature. मैंने आपको मेंडलीव का एग्जाम्पल दिया था. Why I gave you that example? Because of this predictive nature. That once you do something on using say DST, you are able to predict certain things which maybe experimentalists is not imagining. Now, what is happening in the case of machine learning? What people are doing that by using machine learning, they are not able to predict say one structure. They are able to predict a series of structures and they present those to the experiment. They say, see, out of this, I think this is the most probable structure which you are going to find. And these kinds of properties you can really get. Why material scientists are so important now? Because they are actually tailoring materials for various purposes. आपको सेंसर बनाना है, I have predicted one material which can do this task. You have to make say a filter, I have a material, you can use it for doing something. So now you can see the synergy which happens between the computational scientist who is doing material science and actual person who is going to do the experiment in the lab itself. So this is there in silico, in situ or in vitro approach we call in the traditional sense of things. Next slide. Now the history. John Poppel was from mathematics, Cohen was from physics, and Levitt was a computational biologist. Schwarzschild was a chemical physicist. Karpolov was from chemistry. Interdisciplinary thing is happening. Excellent. Now, that is what I am trying to emphasize. It is that something which you are learning here in this workshop. You will find that you can collaborate with your chemistry friends. You can collaborate with nanotechnologists. You can collaborate with very many people around to do certain things. आजकल हम जैसे for example बात कर रहे हैं energy materials. We want energy materials which we should be able to use for creating solar cells. How can we do that? We are talking of production of hydrogen. How can we do that from water itself? हम वो जो कौन से वाली ट्रेन की हम बात कर रहे हैं, एक तो वंदे भारत है ना, एक और मेल, उसकी बात कर रहे हैं जो हाइड्रोजन ट्रेन की, शिमला काल का रेल को चलने वाली है हाइड्रोजन ट्रेन. तो people are actually focusing on those things. So ओपन जो था ये बिगनिंग में ही 50 के डिकेड में ना एज ए मैथमेटिशियन केमिस्ट्री डिपार्टमेंट में, और वहां आके अब देखिए आप आज हम इमेजिन भी नहीं कर सकते कि केमिस्ट्री डिपार्टमेंट में मैथमेटिक्स वाला जाके बैठे या मैथमेटिक्स वाले डिपार्टमेंट में कोई फिजिक्स वाला जाके बैठ जाएगा या फिजिक्स वाले डिपार्टमेंट में कोई केमिस्ट्री वाला आकर के बैठ जाएगा. बट these are the things because you know something interesting is happening at the interfaces of disciplines, and that is where we need to actually collaborate. That is where we need to really come together. इसकी डिग्री जो थी वो मैथमेटिक्स में थी और ये जॉइन ये डिपार्टमेंट एज ए मैथमेटिशियन और वहां पे एक ऑर्गेनिक केमिस्ट था, उसने इसको एक बात बोली you should not call yourself a critical chemist until you have discovered something about chemistry that other chemists don't know already. क्या नहीं? जैसे होता है ना बार में आगे आप यहाँ पे उठ के क्या करोगे आप तब तक अपने आप को केमिस्ट मत होना जब तक आप केमिस्ट्री का करना बड़े चैलेंज इन his own words, while I am sure I defended my status, this provoked some soul searching and led me to pose to myself the question. What was that question? Now here comes the essence of quantum mechanics. How can quantum mechanics, as we know it in 1952, this is in 1952, be turned into a practical procedure which they applied to current organic chemistry problems in the immediate future? This was no doubt an ambitious target, but the formulation of difficult objectives is always a healthy exercise in any research career. बहुत important बात है लास्ट के बाद कि अगर आप कोई रिसर्च प्रॉब्लम पे काम करने जा रहे हो ना आसान प्रॉब्लम मत ढूंढो डिफिकल्ट प्रॉब्लम ढूंढो और दैट इज ए वेरी गुड एक्सरसाइज हेल्दी एक्सरसाइज इन रिसर्च करियर मैथमेटिक्स से डोनेशन हो रही है एम अपना बड़ा क्लियर है क्वांटम मैकेनिक्स यूज करनी है आफ्टर ऑल इट इज ए मैथमेटिकल थ्योरी ओनली तो कॉन्फिडेंस है मुझे आता है डिफरेंशियल इक्वेशन को सॉल्व करना Let me see whether I can solve it on the computer or not. Hartree theory already काम कर रही थी, Hartree Fock theory लोग काम कर रहे थे. Let me see whether I can apply that. Next. So John Popper developed a famous question which has become a part of knowledge toolkit of a chemist, a physicist, a chemical engineer, a pharmaceutical engineer, and many other people who deal with these. यदि अब मॉडर्न केमिस्ट्री डिपार्टमेंट में जाओगे अगर उनके पास गॉसियन है तो बोलेंगे यार ये क्या काम करते हैं ऐसे वो ब्लैक बॉक्स की तरह बट देन योर इमेजिनेशन ऐड समथिंग टू दैट ब्लैक बॉक्स टू डू वंडरफुल ब्यूटीफुल एंड देन मिशेल लैरे इन हिज नोबेल लेक्चर gave this slide. This is very interesting slide. और इसमें ना आप यहाँ पे ध्यान से जो आपको देखने वाली चीज है वो है at what time people were talking about these things. And these are even now relevant. Like for example, Hooke's law. ये हमारा पोटेंशियल है केमिस्ट्री वाले इसी को यूज करके बोलते हैं हाइड्रोजन मॉलिक्यूल कैन यू इमेजिन दिस एज नथिंग बट ए हार्मोनिक ऑसिलेटर इफ हार्मोनिक ऑसिलेटर इज देन योर Hooke's law is nothing but the potential which you are making. Torsion angle और नॉन बॉन्डेड पेयर्स में ये बड़ा फेमस 612 पोटेंशियल है इसको हम लिनार्ड जोन्स पोटेंशियल भी बोलते हैं इसको एट द बैक ऑफ इट इज ऑल इलेक्ट्रिकल व्हाट यू कॉल concepts which come into this loosely put it is all electrostatics which we are talking about and then this is one upon our law famous Coulomb law we are talking about that. So this was the potential that people were talking about. ये वही रहे हैं, ये नहीं बदले हैं. जब भी आपको कहीं पोटेंशियल यूज करना है कहीं आपको तो आप इनमें से कोई यूज करते हो. This is what you are going to do. For example, Lennard-Jones potential was a potential which air Rahman. He took this potential, found the derivative of this, found the forces with the help of the force equation. He solved it for finding positions and velocity. So now you can see कि वो जो पिछली चीजें भी हैं वो कैसे आज के प्रेजेंट कंटेक्स्ट में ना आ रही हैं हमें सामने नजर आ रही हैं. Let's go to the next one. Now I think in this particular workshop people are going to do at least one simple experiment in which they will talk about say making of say hydrogen molecule and predicting something on the computer using this extra code or maybe using machine learning. For example, इसमें सबसे important part क्या है जो हम देख सकते हैं? One is this that what is the bond length in the case of the hydrogen molecule? Can I predict that? And do I find that this bond length actually matches with the bond length which people have found experimentally? If I will be able to do that, I think I will know that this is a kind of success which you are going to get if you get into this kind of thing. So this is a very standard curve which you actually talk about, where you actually talk about total energy व्हाट इज इंटरएटॉमिक डिस्टेंस का बड़ा फेमस टर्म है, +2 में बता देते हैं टीचर इसको। But now we have drawn it by taking hydrogen atom, single species, उसके atomic number क्या है, what kind of a pseudopotential will go in it because this specifies the pseudopotential code, and how you are able to predict the correct value of the bond length with that. One simple success story which will actually explain you all the elements of doing a simulation. You can always learn everything. What goes into it? कौन सा pseudopotential चाहिए? Pseudopotential को टेस्ट क्यों करना जरूरी है? Convergences कैसे देखते हैं? Is my simulation running properly or not? Can I really? I can learn everything with that. जो convergences हैं, K point की convergences की हम बात करते हैं. How do we see all those things? You can always play with those numbers, try to see how your predictions are getting changed. Which number is playing what role? In doing simulations, one of the most important things is what? Knowing and having confidence that what I am doing is correct. For example, if I have to use a pseudopotential, which I have say generated myself, one of the first things which we do is make that pseudopotential, try to do some calculation which is already done and whose experimental results are known to us. See whether you are getting the right results with the help of that simulation or not. If you are not getting, तो आपको फिर सोचना पड़ेगा कि मुझे कहाँ पे क्या चीजें चेंज करती हैं और उनका अफेक्ट कहाँ पे होता है, कहाँ पे जाकर के वो हमें चीजें बताएं. And that is what the basic goal of this workshop is. Next. Let me don't worry about it. This is just because we are using a different software to project this. I am just coming back to the story of graphene and the way we went ahead with these kinds of calculations. It was I think in 2004 that a paper was published regarding graphene. Or around 2010, I don't know if I'm not wrong, we could get a Nobel Prize for him and his friends. 6 साल में इतनी जल्दी नोबेल प्राइज मिलना कोई बात नहीं. हमारा भी उसके ऊपर थोड़ा इन्वेस्ट करने लगा, भैया पूरी सिस्टम है. इसका मतलब है अब जो हमारे पास लैपटॉप है और जो हमारे पास कोड है, maybe we can use that code for studying 2D में. We were knowing what are in the pocket, क्या हमें मिल सकता है और क्या हमें नहीं मिलेगा. Freely open source, Fiesta open source, pseudopotential generation का code open source, everything open source. And we said why not use it? अब ग्राफीन जब हमने इससे काम करना शुरू किया, लोगों ने ना बैक करा करके उस पर काफी कुछ कर लिया हो, फिर भी हमने उसमें से कुछ काम करने की कोशिश. It was actually 2012 that I got a mail from one of my friends in Taiwan. बड़े अच्छे मित्र हैं ना, हंसी मजाक भी काफी कर लेते हैं. तो he had sent me that एक ना मटेरियल है, बड़ा इंटरेस्टिंग मटेरियल है, मोनोक्लोनल साइकिल का. ये मटेरियल है ना, इसमें नोबेल प्राइज मिल सकता है. See what a name she was talking. मैंने मेल बड़ी संभाल के रखी थी. मेरे साथ डॉक्टर अशोक is going to come and give a lecture. He was doing something on silicon and he was trying to put some on the surface of the silicon. Paper publish हो गया था. I told him, yeah, let us leave everything else, let us concentrate on polyethylene disulfide. ये स्टोरी polyethylene disulfide के साथ शुरू और हमने इसके ऊपर एक पेपर जो स्टडी किया, उसमें हमने जो बेसिक स्टडी करी थी वो ये था कि स्ट्रेस और स्ट्रेन लगाने से इसकी प्रॉपर्टीज के क्या फर्क है. एंड वी सॉ इन बैंड स्ट्रक्चर दैट हमारे पास अगर कोई जो बैंड स्ट्रक्चर है उसमें जो बैंड गैप है वो डायरेक्ट है या इनडायरेक्ट है, वो ट्रांजिशन कैसे होती है हमने प्रेडिक्ट किया. दिस वाज दैट पेपर. नेक्स्ट और एक बार और चलाना. दिस वाज दैट पेपर एंड वी फाउंड दैट वाज ऑब्जर्व्ड एक्सपेरिमेंटली आल्सो. तो मैं जो आपसे बात कर रहा था, what doing a prediction and waiting that somebody will do that experiment and will be able to get us some maybe correction or the truth of our prediction. And if that happens, that's just wonderful. This paper got very fast citations of it. आज की डेट में ना इस पेपर की 700 citation. एक single paper, very large number of citations. So this is what happens when you start thinking, what are my resources आज की डेट में और मैं उसमें कैसे काम कर सकता हूँ. And जब आप नेटवर्क करते हो ना, तो नेटवर्क में आने के बाद आपको ना लोग आइडियाज भी देते हैं कि ये प्रॉब्लम है जिसके ऊपर आपको काम करने की. How do you know that there are certain habits which you must basically generate to keep track of all these things? And these habits are जैसे मेरे पास कॉलेज में जर्नल्स की एक्सेस मान लो नहीं है. What will I do? Either I will try to get those access from my friends in the universities or in IITs or in IITs, etc. Or I will go to archive.org. And I will make it a habit. This is मेरे पास एक वो आता है ना न्यूज़पेपर जिसकी मैं हेडलाइन देखता हूँ. Every day I will open that archive.org and those things in which I have an interest, वो मैं चूज करके उसको देखता हूँ कि क्या हो रहा है क्या नहीं. कोई नई चीज आपको नजर आती है, see whether you can work on that or not. That is very very important. So when this molybdenum disulfide was being talked about, we were actually seeing that kind of a thing which is happening. Can you see here these arrows? They are indicating कि monolayer में ये हमारे पास है direct cap. Whereas when I go to the bilayer, then I have got an indirect cap. Visualization is very simple. And what are band structures? If somebody asks me in common language, what is band structure? I say this is nothing but a fingerprint of the material. This is nothing but that, and that is why we are interested in it. Its properties क्या and this is, I think, something which we can make. And इसके बाद देखिए इस टेबल की citation ये आप देख रहे हो K.S. Novichilo. He was the one who got Nobel Prize with Andre Gide. उसने हमारे टेबल को साइट कर. अब कोई अगर नोबेल प्राइज विनर उसमें कुछ मेरिट देख रहा है ना, so that actually gives us a strong sense of, I should not use this word, but saying कि अपने आप को शाबाशी दे दो यार, बहुत अच्छा काम किया है ना. So do remember one thing, we must learn to अपने आप को भी शाबाशी देने की कोशिश करनी चाहिए. कई बार लोग शाबाशी देने भी नहीं आएंगे, है ना. हमको लर्न करना चाहिए. वेरी गुड Mr. Ahluwalia, you have done a very good job. Your team has done a good job. So this is what is the picture which starts looking at. ऐसे ही ये और भी थे WSC2 में काम करा हमने, उसकी भी प्रोडक्शन हमको मिली. Look at the team of experiments who were working. हम लोग दो ही थे काम करते थे सॉफ्टवेयर, लैपटॉप पे काम करते थे. एक हमें फिफ्थ में वर्क स्टेशन मिला हुआ था. अरुण इज गॉन आउट. तो अरुण ने उस वर्क स्टेशन पे लिनक्स ऑपरेटिंग सिस्टम डालना, सोलर से जनरेट करने, फिर प्रॉब्लम्स को सिमुलेट करने की कोशिश करनी, अंडरस्टैंडिंग कन्वर्जेंसेस, what are involved. From there we should be able to and let me tell you another thing. These workshops are very important because when you go to individuals, that tell us बोलते टाइम नहीं है बताने के लिए. If you have come here to learn something. Make best use of it. क्योंकि आपके पास वो लोग हैं जिन्होंने इसको इस्तेमाल किया है and you are willing to share those things. Otherwise लोग willing नहीं होते हैं कि वो share करें. Next. So these are some of the things which were experimentally also found. Next. So this was what I was talking. ये जो पुराना है काफी citation का जो आया है, ये 2012 में पब्लिश हुआ था और इसकी ना citation आज तक जिसके मैं बता रहा हूँ लगभग 700 citation है. Next. So this is again a problem with the system. Ashok, who is going to be here. Dr. Jagdeep is my collaborator. Dr. Chris Mohan, Dr. Manish Sharma, Dr. Surjeet is part of your college itself. So you have wonderful people, you know. मैं जब ये बोल रहा हूँ ना wonderful people, I am saying that they are scientists who can compete in the world. I'm not talking of India. I'm not talking of Himachal Pradesh. तो हम इस अपॉर्चुनिटी को कैसे इस्तेमाल कर सकते हैं, कैसे हम यूज कर सकते हैं. डॉक्टर राजेश, उन्होंने कार्बन चेंज पे बहुत अच्छा काम किया. Then we have here with us Neha sitting, Dr. Neha. He has also done beautiful work on retrostructure. तो हमारी जो टीचर्स है ना, उनकी स्ट्रेंथ क्या होती है? हमारे स्टूडेंट. मैं अकेले कुछ नहीं कर सकता. One student comes and keep us, you know, encourage. इधर हम आपके साथ हैं, है ना. और स्टूडेंट को हम बोलते हैं बेटा हम भी आपके साथ हैं. That is how it all happens. So here are my collaborators. Pandit, आप lecture देंगे. Professor Ravana is from NPS, Professor Kankishwar, Professor Raman, Dr. Ashok, Jagdish, Anil, Shamchan, Neha, Professor अधिकारी के साथ भी recently कर्म का काम पब्लिश हुआ है. So we have a good network of people. और मैं तो बल्कि मुझे तकरीबन 8 साल हो गए हैं रिटायर हुए, बट इनके साथ मिलके ऐसा लगता नहीं है कि हम रिटायर हैं. अपने मस्त रहते हैं, इनके साथ गपशप मार लेते हैं, ज़्यादा वक्त है, and we enjoy, you know, learning from each other. Though my goal is getting decreased day by day, but I still enjoy their success, and I wish them great success in future. So thank you very much, sir, for I'm so grateful that you invited me to interact with a young audience, which is the future of the country. Thank you.
Any question?
Yeah.
If anyone wants to ask something,
आज मैं यहाँ हूँ शाम तक, ठीक है. फिर लंच टाइम पे भी मिलेंगे. आपकी कोई बात करनी होगी आप प्लीज आके बात कर सकते हो मेरे साथ. If not immediately, most welcome. Right? Okay.
Your talks have been very interesting. आवाज आ रही है? आवाज आ रही है? हेलो. Sir, your talks have always been very interesting. But today you have chosen a very good talk. It suits very good today. I am wrong. I think today is quantum day, so it will be a tribute to Max Planck. Planck's constant was, I think, discovered on this day. So after that, it is just quantum day. So if I am not wrong, then there is an announcement. In front of the old campus, will be having a photograph with our today chief guest. So afterwards, we will be having lunch just opposite to our new campus, that is in the boys hostel. Thank you very much. Our faculty will be accompanying you.
the new campus, right? When Madam Rekha wants to discuss.